Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting our first lecture of fifth week for the course of wireless and mobile communications. In our last lectures, in fact, in last 3 weeks, we discussed some important concepts related to wireless communication, and those concepts were primarily focusing on the cellular architecture of the wireless systems, how cellular architecture enable us to improve the overall capacity of our wireless network. Moreover, we discussed the related concepts regarding the cellular systems, and another important aspect that we discussed was related to trunking, how we use trunking theory to determine how we can optimize the channel capacity while maintaining a specific grade of service. Actually, whatever discussion we had made until last week, that was related to chapter number 2 of our textbook, which was related to cellular concepts. In fact, this is chapter 2 in second edition of Rappaport's book, and if someone has third edition, in that edition that was chapter 3. So basically, from today's lecture we will be starting a new chapter with respect to our textbook, and that chapter is related to the mobile radio propagation, and is focusing on large scale path loss. This one is chapter number 2 for our textbook, chapter number 3 for our textbook, and if someone is using third edition of the book, so it will be chapter number 4 for third edition. So for this chapter we'll be focusing on the large scale path loss modeling for the mobile radio propagation. Before we start discussion on large scale path loss, I feel that it is important to elaborate why we need the propagation modeling, why we need to establish relationships related to the wireless propagation or channel properties. So channel modeling, wireless propagation modeling, all these terms we use for this thing, these are very important aspects for wireless communication. Why we need this type of modeling is related to the nature of wireless channels. Whenever we design a wireless system, the wireless channel places a limit on the performance of system, because the actual medium which has to be used for propagation is actually wireless channel. And if we have a poor quality channel, or if our system mismatches with the properties of wireless channel, in that case the system will not perform good. So in order to ensure the performance of a wireless communication system, we need to design a system in such a way that it meets the requirements of channel, and and for that we need to analyze, or we need to characterize the properties of the channel. How does the channel affect the signal when it passes through that particular wireless channel? There are few things related to wireless channel that are of significant importance. First of all, the wireless channel, they have a random behavior. Unlike wired systems, which are mostly deterministic, the behavior of wireless channels is fairly random, and it's because the channel itself is changing. Generally, the properties of channel, they are not fixed, and with the time they are also changing. Similarly, since the properties of channel are changing with time, in that case the characteristics of channel are also changing with time. So wireless channels, they have this property of randomness as well as the time dependence, which is not common for the wired system. Secondly, because wireless medium is unbounded, whenever a signal is placed in a wireless medium, it can propagate in any direction, and before before reaching to the receiver side, it may take variety of different paths. So what happens if you transmit a pulse from the transmitter? It can take like maybe 10 paths and reach the receiver from 10 different paths. So at the receiver side you will be receiving multiple copies of the same pulse which are received through different paths. So one of the important aspect of the wireless systems is the multipath propagation properties. So it's associated with multipath. As compared to wide medium, the wireless channel are less reliable as compared to wide medium because of these properties. One of the important aspect for wireless system is the effect of mobility. Not only the mobility of the user equipment, but also there are different entities which are mobile in the wireless system. For example, if a car is moving in the system, eventually any signal which is being reflected from that car would change. So any movement in that wireless system would also impact the signal levels. Signal, when it passes through wireless system, it experiences different phenomena related to electromagnetics, and those phenomena are reflection, scattering and diffraction. So each signal going through a wireless channel, it undergoes any of these or maybe all of these. Eventually this also degrades the performance of wireless system. From this discussion you can see that the channel is actually a random entity in overall wireless system, and it's important to characterize how a channel would affect the signal in order to ensure the performance of our wireless communication system. This is the illustration of a typical wireless environment. You can see that once a signal is transmitted from mobile, it can take variety of different paths. We may have some distant hills or some remote reflectors which may reflect back the waves which are going in that direction. Local scatterers, local reflectors may also reflect the waves. So if a signal is generated, say for example a mobile is here and it wants to communicate with the base station, so whatever signal is generated, it may take variety of different paths. Say for example it gets reflected from this building and goes to the base station, it gets reflected from other building and then gets again reflected from this hill and goes to the base station and so on. So this base station would be getting multiple copies of the same signal. Similarly, if another co-channel mobile is at some other location, so it will be generating the similar sort of effect. So there will be variety of different copies of the signal which will be received at the base station. So it's a typical environment how the wireless propagation is obtained in the free space, and how does multiple signals they go to the receiver side by getting reflected from and scattered from variety of different objects available in that medium. So so the question is how we need to do the modeling. First of all, the most important thing that we now understand that it's very important or critically important to model the propagation environment so that we can achieve the desired performance of our wireless system. This wireless channel modeling is actually one of the toughest part in the system design because of the inherent random and unpredictable natures of the wireless system. In most cases this modeling is based on the probabilistic analysis, because of the randomness which is available in the wireless channel. So we need to use probability theory, and on the basis of that probabilities we generally come up with the averages or statistics of the signal. So how a wireless system would behave on an average basis, in order to predict the overall performance of the wireless system. As I said, the modeling is actually a probabilistic in nature. So most of the wireless model, they are based on measurement. So if we need to model the wireless channel in a particular environment, we take up a measurement campaign in order to estimate how does a signal would behave when it passes through that particular wireless environment. As I said, a wireless system is actually random in nature, so we observe different times of different scales of variations in the signal which occur when it passes through a wireless communication. So generally we divide those variation in two major categories. One is called large scale variations, and second one is called small scale variation. Although this chapter is focused on the large scale variations, but we'll be getting some basic introduction regarding the small scale variation, and we'll have detailed discussion when we start our next lecture or next chapter. So large scale variation, what does large scale variation means? We observe these are the variation which are observable when we observe them over a larger distance, which is actually much larger than the wavelength. For example, if I ask you how much would be the power after 10 kilometers, so 10 kilometers is a fairly large distance. So how much power variations we observe is an example of a large scale variation. Actually, large scale variation, it is divided into two major categories. One is called path loss and second is called shadowing. Path loss is actually refers to the losses which occur during the propagation of the wave. In other words, how much power is lost during propagation. So when we focus on path loss, so generally we see how much power we'll get at the receiver side in comparison to the transmitted power, and how much power would get lost during that propagation. Shadowing is actually refers to the random variation in the signals which occur at relatively large scale. One thing I must mention, that path loss is in most cases is deterministic, and we can estimate how much power is lost during propagation, but this shadowing is random because its randomness is around the path loss. So this randomness occurs when the signal pass through different cluttered environment or different through buildings and stuff like that, so that they cause some variation in the received power. Small scale variations, these are related to the variations that we observe at very short distance, which are comparable to the wavelength of the wave, or the variations which are related to the small time duration. For example, you must have noticed that it may happen if you try to make a call and you see there is no signal in the that you receive, but if you wait for a second or maybe a few seconds, you will see that the signal strength goes to maximum, so you get the full signals. So it happens is this variations, although you haven't moved from here, so within a small duration of time, or if you may have moved a little bit within a small movement, you can see the variation goes from very small value to the very large value. These are generally known as the small scale variation. These variations, they actually occur because of the multipath propagation and motion in the system. So because in wireless environment the multipath is unavoidable and also the motion is also there. So these effects, this effect of motion and multipath propagation, they cause the variation in the signal strength in this small scale. So let me quickly discuss what are these path loss. What is the path loss modeling? So when we use the term of path loss modeling, basically we are referring to the scenario where we try to calculate or relate the received power when we know the transmitted power. So we try to relate the received power with the transmitted power, provided we know that how far we are from the transmitter. So this path loss is generally calculated by some theoretical analysis. We have certain types of theoretical analysis that we'll be discussing in this chapter. But this path loss is also calculated on the basis of measurement based schemes. So sometimes we make tons of measurement in a certain environment, and then we make a model on the basis of those measurements to estimate the path loss. As I said, path loss is basically deterministic. So if you know the transmitted power and you know the distance, you can easily calculate path loss as well as received power. From the receiver point of view, actually the path loss modeling enables us to calculate the average value of the received power. I must emphasize on the term average, because as I said, there are certain randomnesses in the system, but when we calculate the path loss, so generally we are focusing on the what is the average value that we will be getting at that particular distance. Second thing is shadowing, which is also a type of large scale modeling. Shadowing, actually it refers to the random variation even if you are at the same distance, but because of the different types of environments at different distances, we see some variations. So for example, if at a distance of 1 kilometer you are getting, let's say for example 1 watt of power, and if you move at another location, still the distance remains the same from the base station of 1 kilometer, you may observe that you will be getting some different power, maybe 1.1 or 1.2. That difference in power is actually because of the effect of shadowing, because the signal has to go through the environment, and that environment also causes those randomnesses, those randomnesses they account for the shadowing effect in the wireless propagation. You may have noticed that when you are in open environment where there is no building, you get better signals, but if you come in between the buildings, you will see the decrease in the received power. That decrease is because of that cluttering environment, and cluttered environment because of the presence of building, and that cluttered environment generally cause the shadowing based randomness which we observe in the received signals. Small scale model, as I said, they are observable at a very short travel distances. These are generally known as fading models. So these fading models are referred to rapid fluctuation in the received signal strength when we travel small distances or we observe the signal for a short duration of time. How does this variations occur? Actually, as I said, the signal in wireless environment, it has to come through with a multipath propagation. So when we receive the signal at the receiver side, we observe that there are different components of the signal which are being received, and when we add them together we will get the total signal. But because those signals are coming from variety of those multipaths, so sometimes that addition is constructive, so giving a very high amount of power, but sometimes that addition is destructive, giving very low amount of power. So even if you are at the same position, you may be receiving a very low amount of power, or after some time you may be getting very high amount of power. So basically this small scale variation occur because of the random addition of those different components which are coming from different multipath environments, and you can see at different points you may be able to see a significant amount of difference between received power. 30 to 40 dB difference can be observable when the mobile moves for a very short amount of distance, or we wait for a short amount of time. This is a graphical illustration of these three different phenomena. This blue line here is actually showing a path loss, and you can see that it's kind of deterministic, is gradually decreasing, because as we go away from the transmitter, the received power strength would get decreased. So this can be calculated from measurement or theoretical formula. If you see, there are these black lines, they are random, and this kind of randomness, they are actually occurring at a large scale. So if you move at certain distance, so you will see the variations in the received signal, which are represented by this shading. This dotted line is actually superimposed impact of the multipath fading or small scale fading. You can see that this causes a significant variation in the received signal. At some point you may be having a very high amount of power than expected through path loss, and at some point you may be getting very low amount of power, which is sometimes known as deep fades. So at some points we may get deep fades, and the signal strength gets very low at those points. So these are the different modeling parameters that we use in the wireless propagation environment. And okay, we now start our discussion regarding the basic propagation mechanism that we encounter when in the wireless propagation. When a signal goes through a wireless environment, it get affected in three different ways. First one is the reflection. You can see whenever a wave hits a large object compared to wavelength, it reflects back to the original medium. So for example, if a signal is transmitted from this vehicle, so if it gets reflected from this wall and goes back in the medium. Diffraction is also another phenomena which occurs when the wave passes close to a sharp edges, like the edges of a wall or rooftop, stuff like that. For example, this edge, this corner here, it will cause diffraction. In diffraction, a wave which goes through diffraction, it gets bended. For example, if a wave is coming from this way, so from this corner it gets diffracted, so it will bend like this. So this bending is useful in a sense that from diffraction a user here can also get the signal, but it's problematic in the sense that the diffraction generally is associated with a loss. So generally whenever there is a diffraction like at this corner, so eventually there will be a loss in the signal as well. Scattering is a third phenomena which relates to the irregular reflection from a small objects. For example, if a wave gets strike to a small object, so it will scattered in different directions. It will go like in different directions. So this scattering is called is the scattering phenomena, which generally disperse the wave energy in different directions because it's because of the irregular reflection occurring at that small objects. Okay, now let us start our discussion related to the path loss modeling. Actually, as I said, path loss modeling is important to estimate how much power we expect to receive at the receiver side when we transmit certain amount of power from the transmitter. And this path loss modeling, it is done for outdoor propagation as well as for indoor propagation as well. So there are different models for outdoor propagation as well as we see different models for indoor propagation, because whenever we need to model signal, we want to estimate the power for both cases, for outdoor and indoor cases. There are variety of path loss models which are available in literature. Although we are not going to discuss all those models, but we'll discuss few examples of specific models which are based on which can be characterized as two major categories. First one is the theoretical or mathematical based model, which are based on some mathematical analysis or physical foundations. Second are called measurement based or empirical models, which are based on a measurement campaign by which we take lots of measurement in certain area, and then on the basis of those measurement results we make a model to calculate the path loss in that particular environment. Theoretical based models will be discussing free space propagation models, two-ray ground deflection model, knife edge diffraction model, log distance path loss model. For measurement based model we will be discussing Okumura model and Hata model, and if time permits we may discuss some more models as well. However, I must mention that these are not the comprehensive list of models. In fact, there are different models available for different types of propagation environment and for different types of frequencies and for different types of cellular system. These models, what we are going to discuss here, they are only to provide a basic understanding to the students regarding the path loss. Okay, let us start our discussion on free space propagation modeling. Free space propagation modeling means we are focusing in an environment where there is no obstruction. So transmitter and receiver, they are placed in an environment where a clear line of sight communication path is available between them, and there is no other objects in the vicinity which can obstruct the communication between transmitter and receiver. An example of line of sight communication link can be satellite communication system, where the satellite in space, they communicate directly to the earth station at an open space. Similarly, microwave links which are available at different places, they are generally placed at very high towers which are above the normal buildings. So those towers, they are aligned with each other to provide a line of sight radio link. So in this case, this is the ideal case where we are not using the signal is not obstructed by any of the obstacle in the path. The free space power which is received at the receiver side is calculated by using free space equation, which is given here, the received power PR d, this d shows that we are calculating power at a distance d from the transmitter, is given by this formula, where this pt is the transmitted power, gt is actually the gain of the transmitter antenna, gr is the gain of the received antenna, lambda square is wavelength of the wave which is being used, 4 pi, they are of course they are constants, d square, d is actually the distance which is represented as transmitter and receiver separation, or TR separation. This L is actually refers to the losses which are present in the system. See, there are two types of losses. One is the one which we will be calculating from the free space propagation model. This is loss related to the propagation. When the signal propagates from the free space, how much loss will be there, so that will be calculated from free space. But generally the system encounters other types of losses as well. For example, when the signal goes through the connectors in the transmitter or receiver, they experience some loss. Similarly, the amplifiers, they may, or attenuators or other components in the system, they may give certain loss in the system. So eventually that loss, the total loss, which is system generated loss, not related to the propagation, is included in this entire term L. For simplicity, for this case, because we are only focusing on the propagation and we are not focusing on the system generating loss, so we will take this L to be equal to 1. So this term will vanish from this equation. However, if there are losses, so we would be required to reinsert this term to include those losses. So this is a free space equation which is given by this formula, as I mentioned earlier. The antenna gain is also related to the effective aperture of the antenna by this relationship. This is a general relationship for antenna gain. The effective aperture AE is related to the physical size or physical dimension of the antenna. Lambda is a wavelength, and as I said in initial lectures, then in wireless communication we generally focus on frequencies rather than lambda. So we can, if we want, we can represent this expression in terms of frequency as well, by a simple relationship that lambda is c divided by f, or we can write it as 2 pi c upon omega c, where f is the carrier frequency of wave in hertz, and omega c is the carrier frequency in radian per seconds, or cyclic frequency. C is the speed of light, as we know, which is 3 into 10 raised to power 8 meter per second. So this is this free space equation. You can see that this equation relates the transmitted power Pt to the received power Pr here. Typically gains GT and GR, these two are dimensionless quantities. They do not have any specific dimensions, so these are dimensionless. D is the distance and lambda is the wavelength, which are in same dimensions. So eventually whatever unit for PT or transmitted power we use, we will get the same unit for received power PR. So if we are taking transmitted powers in watts, so we will be getting the received power in the same unit of watts. The miscellaneous loss L, as I said, they relate to the losses due to transmission line attenuation, filter losses, antenna losses, and so on, which commonly encounter in the system. But for simplicity, we are assuming L is equal to 1, which indicates that there is no loss caused by the hardware. So there will be propagation loss due to the propagation in the free space, but there is no other loss by the system hardware or different components of the system which are reflected by this value of L is equal to 1. One important thing you should note from the Friis equation is that this power, received power PR, is inversely proportional to the distance squared. So this PR is actually varying with respect to square of the TR separation. So if we increase the separation, the power would get reduced by square of the value, whatever increase we see in the distance. In order to give you a better insight on this equation, let me rewrite the Friis equation by combining different types of terms which are common to each other. So combining these related terms, you can see that this PT, GT, these two terms are actually related to the transmitter. These two are transmitter. The second bracket GR, this one is related to the receiver, and this entire thing, this is actually related to the propagation environment, where we have effect of the wavelength as well as the effect of distance. So actually this free space equation, it can be seen as comprising of three different components. The first part, which is generally named as effective isotropic radiated power, or EIRP, which is product of PT and GT. The second term is actually the receiver antenna gain, which relates to the receiver side, and the third bracket, this entire thing is related to the propagation of the wave in free space, and which is commonly represented as free space path loss term, which gives you the loss, which actually relates to the loss which we encounter when we go through the signal goes through the free space. This first term PTGT, you can see this is actually giving you the total amount of power that you get in a specific direction, because PT is the total power and GT is the gain which is provided by the antenna in that particular direction. So this EIRP would give you maximum radiated power which is available from the transmitter in the direction of maximum antenna gain, and we call it isotropic radiated power because we are comparing it with the isotropic radiated antenna. So if we replace this antenna having gain GT with PT with power PT by an isotropic antenna, so it should have the power of EI, which is equivalent to EIRP, in order to get the amount of power that we are getting from that particular antenna. So you can see that the received power is not only dependent on the effect of the propagation environment, but also it is dependent on the transmitter parameters, which are represented by their EIRP, and also dependent on the receiver parameter, which are represented by the received antenna gain. Okay, so this is the general free space path loss, free space propagation model, which we represent using this free space equation. We will continue this topic in our next lecture by representing this power in decibel values as well, and we'll have some discussion on the specific problems related to this type of scenarios. Thank you all.